Imagine, you're standing on Mars staring at the endless rust-colored landscape. The thin atmosphere barely muffles the sound of your own breathing inside your spacesuit. Far above, Earth is just a tiny blue dot in the sky, separated by over 100 million miles of cold, empty space. Communication with home takes an agonizing 11 minutes, even at the speed of light. 11 minutes to send a message. 11 minutes to get a reply. In an emergency, that's the difference between life and death. But then you pull out a small, sleek device, you press a button, and instantly, without delay, a message appears on your friend's screen back on Earth. No waiting, no lag. Just instantaneous transmission, as if the two of you were standing side by side. Sounds like science fiction, right? A technology ripped straight from Star Trek or Interstellar? But what if I told you, scientists may have just taken the first real step toward making this possible? In a groundbreaking experiment, researchers successfully teleported quantum information between two particles, pushing the limits of physics itself. This isn't just about faster data transfer. This is about defying the very nature of space and time. Quantum teleportation allows information to travel without passing through the space in between. No signal beaming through wires, no radio waves stretching across the void, just instant transmission. The implications? Mind-blowing. A future where data moves faster than light, where quantum computers communicate across the world without a detectable signal, where encrypted messages are truly unbreakable. But is this really the dawn of faster-than-light communication, or is there a catch? Before we dive into the bizarre and mind-twisting world of quantum mechanics, let me ask you something. Do you love unraveling the deepest mysteries of the universe? Because that's exactly what we do here at Cosmic Whispers. Every great journey starts with a few brave explorers. Right now, we're just beginning, and your support means everything. If you enjoy diving into mind-bending discoveries, hit subscribe. It's free, and it helps us grow this community together. All right, let's break this down. To understand how scientists just teleported data, we first need to talk about one of the strangest, most controversial ideas in physics, quantum entanglement. Imagine you have two tiny coins, spinning randomly in different locations. Normally, each coin is independent. Flip one, and it lands on heads or tails with no effect on the other. But in the quantum world, things don't work like that. If two particles become entangled, their fates are linked permanently. Change the state of one, and the other instantly reacts, no matter how far apart they are. It's as if they're connected by an invisible thread that operates beyond our understanding of time and space. This idea baffled even Albert Einstein. He famously called it spooky action at a distance, because in his view, nothing, absolutely nothing, should be able to send information faster than the speed of light. According to Einstein's theory of relativity, light speed is the ultimate speed limit of the universe, but entanglement seemed to break that rule. If two entangled particles could influence each other instantly, weren't they defying the laws of physics? For decades, scientists debated whether quantum entanglement was real or just a weird mathematical illusion. Some believed there had to be hidden variables, some unknown force operating in the background that we simply didn't understand yet. But then in 1981, physicist Alain Aspect conducted a groundbreaking experiment. He and his team used pairs of entangled photons, particles of light, and measured how they behaved when separated by a distance. The results were clear. No matter how far apart the photons were, changes to one affected the other instantly. There were no hidden variables. Quantum entanglement was real. And then came the next big question. Could we use entanglement to send messages? At first, scientists believed the answer was no. While entangled particles influence each other instantly, you can't control how they change. If you measure one particle, its twin takes on the opposite state, but it happens randomly. This meant there was no way to encode a meaningful message, at least not in the way we send information through fiber optics or radio waves. But that's where things get interesting. In the 1990s, physicists discovered a loophole. They realized that while entanglement alone couldn't send information, it could be used in combination with classical communication to teleport data from one place to another, without ever physically traveling between them. In 1997, a team of scientists led by Anton Zeilinger achieved something incredible. They teleported quantum information for the first time. Not physical objects, just information. But even that was enough to turn science fiction into reality. Over the years, experiments became more advanced. In 2012, Chinese scientists teleported quantum states over 60 miles. By 2017, they extended that record to over 800 miles, using a satellite to teleport entangled photons between ground stations on Earth. Every time the results defied intuition. The information wasn't traveling across space in the normal way, it was simply appearing at the destination. And now, scientists have taken yet another step forward. In a recent experiment, they successfully teleported quantum data with greater precision and reliability than ever before. The implications? We may be inching closer to a world where information moves in ways we never imagined, but how did they do it? And does this mean we're on the verge of true faster-than-light communication? Let's dive deeper. Quantum entanglement. Is strange enough on its own, but quantum teleportation? That sounds like something ripped straight from the pages of a sci-fi novel. And yet it's real. Scientists have done it. But to truly understand how it works, we need to break it down. Because what just happened in this latest experiment isn't just another step forward. It's a giant leap toward a future where the way we think about communication, encryption, and even the fabric of reality itself could change forever. So, how do you teleport information without sending it through space? To answer that, imagine a magician's trick. Two identical envelopes sit on opposite sides of a vast canyon, one with a sealed letter inside, the other completely empty. Normally, to move the letter across, you'd have to send it the old-fashioned way. A carrier pigeon, a drone, maybe even a rocket. But what if instead you could destroy the letter in the first envelope and have it reappear instantly in the second? Not a copy, not a duplicate, the exact same letter as if it had never traveled at all. That's the essence of quantum teleportation. It's not about moving particles. It's about transferring their quantum states from one place to another without any physical travel in between. And to do this, we rely on something called the quantum no-cloning theorem. Here's where things get tricky. In the classical world, the world of everyday physics, you can copy information as much as you like. You can write down a message, take a picture of it, even send copies to 100 different people. But in quantum mechanics, that's impossible. The moment you try to measure a quantum particle, you change it. It's like trying to look at a soap bubble without popping it. The very act of observation forces the quantum state to collapse into a single outcome. This is what makes direct transmission of quantum data so difficult. You can't just read a quantum state and send it through a normal channel. But there is a way around this. Instead of copying the quantum state, we can transfer it. And this is where entanglement comes in. Imagine we create two entangled particles. Let's call them particle A and particle B. We send particle B far away to another location, say a lab on the other side of the world. Now we take a third particle, particle C, that contains the quantum information we want to teleport. Here's the trick. We perform a special quantum measurement on particle A and particle C together. This doesn't just measure them. It destroys the original quantum state of particle C. But thanks to entanglement, something bizarre happens. That quantum state is instantly recreated in particle B, no matter how far away it is. It's as if the quantum properties of particle C jumped across space, bypassing the normal rules of physics. The information hasn't traveled in the traditional sense. It has been teleported. And here's where the latest breakthrough comes in. In a new experiment, scientists have achieved the most precise and reliable quantum teleportation ever recorded. They successfully transferred quantum information between two nodes in a quantum network, using an advanced entanglement-based protocol. What makes this experiment groundbreaking isn't just that it worked. It's that it worked with unprecedented fidelity, meaning fewer errors and greater stability than ever before. The technology that once worked only in ultra-controlled environments is now becoming more practical, inching closer to real-world applications. But let's pause for a moment. If this is possible, then doesn't this mean we've achieved instant communication? After all, if entangled particles affect each other instantly, and we can teleport quantum information through entanglement, shouldn't this allow us to send messages faster than light? Imagine using this on a spaceship traveling to another star. Earth and the ship could communicate instantaneously, no matter the distance. Well, not exactly. Here's the catch, the paradox that keeps quantum physicists up at night. While quantum teleportation is instantaneous, it still relies on one crucial step that slows it down: classical communication. Think back to our experiment. When we teleport the quantum state from particle C to particle B, the process is incomplete. The recipient, who now has particle B, needs one final piece of information to make sense of the message, and that piece of information can't be teleported. It has to be sent through a normal classical channel, like a radio signal, a fiber optic cable, or even a handwritten note, and that means we're still limited by the speed of light. In other words, teleportation can transfer quantum information instantly, but it can't be used to send useful messages faster than light. The laws of physics remain unbroken, at least for now, but don't be disappointed just yet. Because while this might not give us instant communication across the galaxy, it does open the door to something just as revolutionary: a new kind of internet, one that could change everything. Let's explore what that means. Imagine a world where hacking is impossible, where no one can intercept your messages, no government can spy on your data, and no supercomputer, no matter how powerful, can break your encryption. A world where banks, hospitals, and even entire nations communicate through a system that is fundamentally unhackable. This is the promise of the quantum internet, and quantum teleportation is the key to making it a reality. For decades, our digital world has been built on encryption, codes, designed to keep our private data safe. Every time you send a message, enter a password, or make an online payment, your information is protected by complex mathematical algorithms. But here's the problem. Encryption relies on math problems that are difficult, not impossible, to solve. Given enough time and processing power, any code can be cracked. And now we face an even bigger threat: quantum computers. Unlike classical computers, which process data using ones and zeros, quantum computers use qubits, particles that can exist in multiple states at once. This gives them an almost supernatural ability to perform calculations at speeds no ordinary machine can match. A quantum computer could, in theory, break even the strongest encryption in seconds. That means that every secret, every password, every piece of classified data ever stored could suddenly be at risk. Governments know this, corporations know this. It's a race against time before quantum computers become powerful enough to shatter cybersecurity as we know it. But what if we fought quantum with quantum, instead of relying on breakable codes? What if we could create a system where hacking wasn't just difficult, it was physically impossible? This is where quantum teleportation comes in, because when you use quantum entanglement to send information, something remarkable happens. If anyone tries to intercept the data, the act of measurement changes it, instantly revealing the eavesdropper. This is the foundation of quantum key distribution, QKD, a revolutionary encryption method that uses entangled particles to create unbreakable communication channels. In a quantum network, users would share encryption keys through entangled particles. If a hacker tried to eavesdrop, they would break the entanglement, immediately alerting both parties. Unlike traditional encryption, where an attacker could secretly record data and decrypt it later, quantum encryption makes spying physically impossible. And here's the most exciting part: this isn't just a theory. It's already happening. In 2017, China launched Mikius, the world's first quantum communications satellite. Using entangled photons, Mikius allowed scientists to perform quantum key distribution between two cities over 700 miles apart. This marked the first step toward a global quantum internet, one that could one day replace the vulnerable networks we rely on today. But now scientists have taken things even further. In their latest experiment, they successfully teleported Quantum information not just between 2 points, but within a complex quantum network. This means we're no longer just dealing with isolated teleportation experiments, we're seeing the birth of a true quantum communication system. Think about what this could mean. Governments, banks, militaries, every institution that relies on secure communication could transition to a quantum internet. Cybercrime as we know it could become obsolete. Intelligence agencies would need to rethink their entire approach to surveillance. The very nature of digital security would be rewritten. But there's something even stranger lurking beneath the surface of these discoveries. Because if quantum teleportation allows information to move without traveling, and if entanglement defies our traditional understanding of space and time, then what does that say about the fundamental nature of reality itself? Are space and time truly separate? Or is the universe hiding something even deeper? Let's explore the mind-bending implications of quantum teleportation and what it might reveal about the fabric of existence. If quantum teleportation allows information to move without traveling, if entangled particles defy space and time as we understand them, then what does this say about the very nature of reality? For centuries, we've been taught that the universe operates within strict boundaries, cause and effect, space and time, action and reaction. But quantum mechanics keeps pulling back the curtain, revealing something stranger, something deeper. The very existence of quantum teleportation suggests that our classical view of the world is incomplete. Let's take a step back and ask a radical question. What is space? At first, it seems obvious. Space is the vast, empty stage where the drama of the universe unfolds. It's where planets orbit stars, where galaxies collide, where light takes billions of years to travel from one point to another. But quantum mechanics suggests that space isn't as fundamental as we once thought. Think about entanglement. Two particles, separated by entire galaxies, yet somehow mysteriously connected. No matter the distance, a change in one instantly affects the other. Einstein called this spooky action at a distance because it seemed to break the ultimate speed limit, the speed of light. But here's the strange part. If entangled particles can communicate instantly, then space itself might be an illusion, something that emerges from a deeper, hidden layer of reality. And if that's true, then what we perceive as distance might not actually exist in the way we think it does. Physicists are beginning to explore an idea called quantum holography, the possibility that space and time are just projections of a deeper, more fundamental quantum reality. Some even believe that entanglement is the very fabric from which the universe is woven. If that's the case, then teleportation isn't just a bizarre quantum trick. It's a glimpse into the fundamental structure of the cosmos. But let's bring this back to something more tangible. What does this mean for us? How could quantum teleportation shape our future? Imagine a world where quantum networks stretch across the planet, making communication completely secure, immune to hacking or surveillance. Banks, governments, and private individuals would have absolute privacy. Elections could be truly tamper-proof. Diplomacy could be conducted in total secrecy, with no risk of leaks. But at the same time, could a world of perfect secrecy have unintended consequences? What happens when even the most powerful agencies on Earth can't intercept encrypted messages? Could criminals and rogue states exploit a system that is unbreakable, even by law enforcement? And what about the ultimate question? If quantum teleportation evolves beyond information transfer, could it one day allow for the teleportation of matter itself? Theoretically, the process behind quantum teleportation, transferring the quantum state of a particle from one place to another, could be scaled up. But there's a catch. To teleport a complex object, like a human being, you'd have to scan every single atom in their body, destroy the original, and recreate it perfectly at the other end. This raises terrifying questions. Would that person still be them? Or would it be a copy? Would consciousness survive the process? Or would the traveler be erased, leaving behind only a duplicate who believes they are the same person? These aren't just science fiction concepts. They're real ethical and scientific dilemmas that future generations may have to face. For now, Quantum teleportation is revolutionizing information transfer, not human transport. But make no mistake, this technology is more than just a tool for scientists in a lab. It's a doorway to a new era of physics, where reality itself is being rewritten. So, what do you think? Are we witnessing the birth of a technology that will change the world? Or is quantum teleportation just another bizarre quirk of nature, destined to remain in the realm of experimental physics? Let us know your thoughts in the comments. And if you found this journey through the strange world of quantum teleportation fascinating, don't forget to like and share this video. Your engagement helps us bring more mind-bending topics straight to you. Until next time, keep questioning, keep exploring, and remember, the universe is far stranger than we ever imagined.